Well, we're back again, and this is the final, the 10th lecture in the Introduction to Radar Systems course. And this lecture will be on radar transmitters and receivers. Here's an outline of the different topics we're going to discuss. Will be an introduction. First, we'll talk about radar transmitters. Then we'll move on to the waveform generators and radar receivers section. And then we'll look about the different architectures that you can put together radar receivers and transmitters in that are available, and their system implications and why they're used one way or the other. And then we'll summarize. Okay, well, here we are, back again for the 10th time at our block diagram. You can see highlighted in this box the sections of the radar system that we're going to talk about today. The waveform generator, where we generate the signal for the first time. It's amplified in the transmitter and then goes out through a device called a duplexer. Whenever you see duplexer, think switch, because we don't want that very large transmitter signal to go into the receiver while we're transmitting, and vice versa. This switch will isolate the transmitter from the receiver. And then also there'll be the receiver section, and the signals will either be going from the transmitter out the antenna, or the received echoes will be coming back from the target through the duplexer and into the receiver. Okay, here's a simplified block diagram of the transmitter, just so you can see it big picture. Okay, and you see that we've got a waveform generator where we generate what's a small signal, and it's generated at usually a lower frequency than we finally transmit, and it's converted up to a higher frequency. But before we do that, we amplify the signal, filter it, and then we go out through the duplexer, a switch. That's you'll see in a minute why that switch needs to be there in great detail. And then out through the transmitter, the echo comes back where it's filtered, and then we amplify the signal, send it into the receiver, and then we digitize it into a signal that we can process and detect the echoes of the targets. The radar transmitters and receivers can be divided into these two important subsections: the high power transmitter section and the low power section. The low power section is, of course, the receiver, because the echoes coming back are very weak. And this just gives you an idea of the size of the signals. The waveform generator signals are very small to begin with, tens of milliwatts to a watt, and then after we upconvert them, there will be a very high power transmitters section where we'll amplify the signal very strongly. It will go from the order of fractions of a watt up to millions of watts, thousands and millions of watts. So that amplifier makes the signal much, much larger. And then the echo that comes back is tiny, very, very tiny. Millionths of a watt, microwatts to milliwatts. And then it is amplified and received, as I mentioned earlier. Okay. Now, with looking at the radar equation, and this is probably the only equation we'll look at in this lecture, I want to focus on the importance of the power of the things that we're going to do in this section. The most important thing we obviously want to do is maximize the signal-to-noise ratio, how strong the target is relative to the noise, and because that's a very strong function of how far we can detect a signal. And we have three things in the transmitter-receiver chain that come into play in the radar equation: the average power of the radar, and then the system noise temperature, and the system losses. And these two down below we want to keep as low as possible. We want the loss to be unity, and the transmitter, the system noise temperature to be low, and we want the losses to be zero, ideally, and we want the power to be infinitely high if we could. The big deal is it's hard to get very high power, and it's very hard to have very, very low system losses. You have to work really hard at these things. So the signal to noise can be enhanced if we have higher transmitter power, if we have low system losses, and we minimize the system noise temperature. Okay? Now let's look at high power amplifiers for a couple of minutes. What are we doing when we amplify the signal? We start off with a very low signal from the waveform generator, and then we amplify usually in a series of stages. The first set of stages are called driver amplifiers, and they amplify somewhat. They don't do the gigantic amplification in the high power amplifier. And we do these with a series because there are limitations to the amount of amplification you can get per stage. And we want to do this with the lowest, have each stage of amplification be with the lowest possible noise and the minimum distortion to the input signal. And it isn't as though one amplifier can supply all of the amplification we need. So we have to do things in stages. Okay? And we also can put amplifiers architecturally different than this set we see in series. We can put them in series and have like a waveform generator, a driver amplifier, and then a high power amplifier, and then the signal going out to the antenna. Or we could take a waveform amplifier, a driver amplifier, and then send that signal, divide it up into a series of high power amplifiers, and then combine the output of these with a summing mechanism, an addition mechanism, and send the signal out the amplifier. Now, so we can use it. We can increase the power by combining signals in parallel. But we're going to have efficiency problems if we do that. We have lower efficiency because there are going to be losses in the combiner here, the high power combiner, and this increased complexity when we do that. In addition, if one of these high power amplifiers has a problem, there can be imbalances between these, and we can get reflection signals going back which require compensation circuits, and there's an increased complexity in the transmitter if we have the high power amplifiers in parallel. But many systems do quite effectively use this technique. This is just to point out that it's one of the downsides of combining amplifiers. Instead of having three stages in series, putting the three in parallel. Okay. There are different types of amplifiers themselves. There are vacuum tube amplifiers and there are solid state amplifiers. We think of, say 50 years ago, there was a cylindrical glass tube, a vacuum tube amplifier that worked in radios. Now, in the 1960s and the late 50s, 60s, transistors and integrated circuits came in, solid state amplifiers, and that allowed us to have things much smaller. But there are upsides and downsides when we build microwave high power amplifiers for both of these. Now, for a long time, we've had vacuum tube amplifiers, and they use different physical mechanisms to do that amplification, and the different vacuum tube amplifiers have different names because of how they're constructed. Some of them are called traveling wave tubes, Klystrons, and that sort of a thing, cross-field amplifiers. Other devices, solid-state amplifiers are just called that. They're made with solid-state, with high-power transistors. The solid-state systems tend to operate with at lower average power, at lower peak power, okay, and with higher duty cycle. And the vacuum tube amplifiers tend to operate at very high peak power and with very low duty cycle. And the cost per unit is very high for these vacuum tube amplifiers. That you can see one vacuum tube amplifier, a traveling wave tube, can cost $500,000. Solid state amplifiers, individual ones, on the other hand, can be in the hundreds of dollars, but for an individual amplifier. But when you package them together in a whole transmit-receive module and look at the cost per watt that comes out, it's quite different. For vacuum tube amplifiers, the cost per watt that you get out of the whole system for the amplifier is at $1 to $3 per watt. But you can, if you're using transmit-receive modules, which effectively are other parts of the transmit too, the solid-state amplifiers can run you up to $100 a watt or more. The size, these vacuum tube amplifiers are huge. They could be a foot in diameter and 3 feet tall, just the amplifier itself, and then they have very powerful power supplies that are many, many cubic feet. The solid-state amplifiers have a very small footprint. The applications, these high-power systems, and as I didn't point out probably enough early on when I'm talking about this, they have very high power, up to a megawatt and more of power output, and the solid-state amplifiers are a few hundreds of watts at most. In their use, the vacuum tube amplifiers are used with dish antennas and with passive arrays, and I'll get into what passive arrays are in a moment when I look at the architectures. And solid-state amplifiers are used in active arrays and digital arrays, so-called another form of phased array system. Now, when we look at the what frequency regimes and what powers are available with today's technology, and this is in rough terms, when you're looking at very high power, very, very high power, the tube amplifiers dominate over the whole microwave region. If you've got to build a radar that's very, very high power, they dominate. Or you're going to pay an enormous amount of money because you're going to have a huge number of solid-state amplifiers. There's a region of competition, and then solid-state amplifiers, and this is talking about on an individual basis, not as a whole system. They'll dominate in the lower power region. Now, of course, you can build systems that have high average power. They take an awful lot of amplifiers to generate that kind of power. Okay, now let's look at some examples. For tube amplifiers, Klystrons and traveling wave tubes are the two most common. And for solid-state amplifiers, they use solid-state power transistors. There's different criteria for choosing a high-power amplifier. Just what are the different ones? If you want average power output as a function of frequency, the bandwidth of operation, the duty cycle, if you're satisfied with a very narrow duty cycle, and a dish is you're going to be using a tube radar, might be just the ideal radar for you, the lower cost. The gain of the antenna, the mean time between failure, etc. It's a very complicated trade-off when you choose one versus the other. Okay. Now, first I'd like to show you an example of a tube radar. This particular radar is at Millstone Hill in Westford, Massachusetts. It was designed in the early 1960s, and it uses a couple of Klystrons, two of them, and it operates at L-band. That's a frequency of about 23 centimeters, about 1300 megahertz, and it's got a peak power of 3 million watts and an average power of 120 kilowatts. That reaches out there. And here's a picture of the dish antenna that's connected to. In the building down here is the transmitter, and you'll see that in a moment. And that antenna diameter is 84 feet. Here's a picture of the transmitter room. Give you a size of the hugeness. The Klystron that is used in this radar costs $400,000 per tube. It's built by Varian. It's 7 feet tall. Here's the system itself. There's a vacuum, the Klystron, and there are coolant hoses because enormous power is going through. Of course, it's not perfectly efficient, so there's a certain amount of heat generated that you've got to bleed off, or the whole system would melt. There's very large waveguide. 200 feet of waveguide goes from the transmitter out to the antenna. There's a 1 kilowatt peak power solid-state driver amplifier. There's a whole room that houses the power amplifier itself. There's a spare tube here, and all sorts of stuff. You can see this is big radar. It has a gain of 42 dB. That's a gain of 10,000 with a low duty cycle. 3% of the time it can be on. Weighs 600 pounds, 7 feet by a foot, just to give you a physical size of the beast. Okay. There are other types of tubes called traveling wave amplifier, TWTs, traveling wave tubes. And here are pictures of 2 of them. They also happen to be built by Varian. One at S-band and one at X-band. And let's just first look. This S-band traveling wave tube, its center frequency is 3.3 gigahertz. S-band, I'll remind you, it's a wavelength of 10 centimeters. And it has a bandwidth of 400 megahertz. And it has a peak power output of 160 kilowatts with 8% duty cycle. Again, around 43 dB, about 20,000 is the gain. And here 4 of them are stacked up and run in parallel, and that were built into an S-band transmitter. And with some of the associated equipment. And this is 8 feet tall for dimensions. You could see they're big tubes. Okay, and here there is an example of an X-band traveling wave tube, coupled cavity traveling wave tube. It's got a gigahertz of bandwidth, 10% bandwidth, peak power of 100 kilowatts with 35% duty cycle. That means 35 kilowatts of power come out of this, and it's got a gain of 10 to the 5th, 100,000. It's got a gain. Wow, powerful animal. Now let's look at solid-state transmitters. Here's one that was built by the laboratory, the Radar Surveillance Technology Experimental Radar. Its acronym is RSTER. It's a solid-state transmitter, and the power amplifiers, power amplifier modules are in this rack. 14 channels of power with 140 kilowatts of total peak power, 8 kilowatts of average power. And you see there's a higher duty cycle than in the other systems. And each channel is supplied by a power amplifier module, 10 kilowatts of peak power. Okay. The first active solid-state radar, active aperture system, is called PAVE PAWS. And this is a picture of that. It's huge, 75-foot diameter. As you remember about phased arrays from the antenna lecture, there are a whole load, 1,792 of them, active transmit-receiver modules, each one with 340 watts of peak power. There are a number, I think it's three transistors in parallel, I believe, 3 or 4. I'm pretty sure it's 3, and they're lined up in parallel. And the transmitter and the receiver are different pieces of the box. And these systems are very reliable. Well over 100, I think 150,000 hours of mean time between failure for this system. And this particular radar is located on Cape Cod, and it does ballistic missile early warning. Okay, and it's built by the Raytheon Company. Now let's talk a little bit about duplexers. Why is the big deal with duplexers? I'll put all 3 lines on here at once. Well, we put out this transmit signal, and then we listen for the echoes. And during that window, we're listening very carefully for an echo that's very small. These little spikes correspond to when we're sampling at a different time delay after the transmit signal. we're listening to see if there's a very small radar echo. We do that for a while, and then we transmit again. Now, and so what that means is we're transmitting for a while, and then we receive. Now, the total time between we start to transmit and we start to transmit again, we call that the pulse repetition interval. But the thing I want to focus on is we do not want this transmit. When we're transmitting, we do not want any signal to get into the receiver. So we want a switch out there, and that switch is the duplexer. Okay, we use duplexer switching to isolate. How much isolation are we talking about? Transmitters typically can transmit peak power signals from 10 kilowatts to a megawatt. Megawatt, think of that. And the received signals can be tens of microwatts to a milliwatt. So we're talking about 90 dB approximately you can have. 9 orders of magnitude. We want that switch to isolate one from the other. If you remember back to the first lecture, we saw that in the chain home radar that the transmitter was located at a different physical location by hundreds of feet. In those days, they weren't great at building duplexers, so they put the transmitter physically distant by hundreds of feet from the receiver in many cases. Okay? So the technology is not easy to make something 9 orders of magnitude of isolation between the transmitter and the receiver. So that's the very important function of the duplexer. Now let's just look about it in a little more detail so it can sink in. Well, when we have the transmitter on, we connect the antenna to the transmitter, and we want to do that without any loss. We want the high power energy from the energy from the transmitter to go right through that switch and out the antenna with no loss. We want to have nothing going back into the receiver. We've got to protect that very sensitive receiver that's used to listening and detecting million microwatts from megawatts and kilowatts. So we want to turn that off. And then on receive, we want to connect the antenna through the duplexer to have a limiter switch to make sure if stuff does leak in, God forbid, we don't fry the receiver. We want the transmitter, of course, is going to be turned off. We want to have an additional, this limiter switch for additional protection, say against strong interference from a nearby signal. And so that's the switching, that's the function of the duplexer. It's got to cut out completely, 9 orders of magnitude, the signals. That's what that duplexer does. So when you hear the word duplexer, you know it's not just like your switch on the light bulb. It's a very different entity. Well, welcome back. This is part 2 of the Radar Transmitter and Receiver lecture, lecture 10, the last lecture of the Introduction to Radar Systems course. Okay. Now let's look at the waveform generator and receiver. Okay. Now what are we doing there? The first thing we're doing is, and we're just going to look at functionally. We're going to generate a waveform, and we've talked about different waveforms where we turn on and we have a sine wave that's turned on for a while and then it's turned off, and the length of that is our pulse width. We call that a pulsed CW signal, and the frequency of the wave inside that pulse is our carrier, the frequency of the radar, So we take that and we generate that frequency down at frequencies that aren't microwave, where it's easy to make a very non-lossy, just exact, with just the right characteristics of stability. We generate that at low frequency, and then we amplify it, and then we upconvert it to the frequency that's of interest to us. And I'm going to talk in a minute what I mean by upconvert. When you say upconvert, I want you to think we shift the frequency, but I'm going to show you how we do that in a minute. Then we filter it, because when we upconvert, we're mixing together the carrier signal with this waveform that we generate, and it generates the the pulse at the frequency that we're interested in, the microwave region. And so what we do is we filter afterwards to get rid of noise on either side of the frequencies that we want to transmit. So we're going to do amplifying and filtering when we do either up conversion, or you'll see in a second, down conversion. Now this is what we do in the transmit chain. On the receive chain, when the very weak signal comes back, the first thing we do is we want to filter out noise that's out of the band of the frequency that we're the carrier frequency. And then we down convert that signal where it's easier to deal with, and we amplify it and put that signal into the analog to digital converter, the A to D, and where we get out our detected output of the size of our echoes, sets of ones and zeros. Each different sample is a bunch of ones and zeros, a number, a digital number that tells us how big the echo is at each sample. Okay? So that's the function of what we're doing. Now, what do we really mean of what we're doing when we're doing up conversion, down conversion, and why? Okay? In the waveform generator, in the receiver, that section, the transmit, we start off with 100 megahertz, a tenth of a gigahertz waveform, say. That's easy to generate, nice and stable. It's got all the right characteristics, and it's very low cost to do. Okay? And then when we up convert, what we do is we have an oscillator that's at that's very, very precise, and in this case 1.4 gigahertz. And when we up convert, we're essentially adding the two frequencies, and what comes out is the sum of the two frequencies. And this device is actually what is known to, if you happen to be an electrical engineer, it's known as a mixer. And when you add two signals together, you get both the sum and the difference of the two signals. And in this case, the up conversion, we're looking at the sum of the two signals. Okay? And so what we get is the sum of the frequency is the sum, or 1.5 gigahertz, which is in approximately the L-band region. And the reason we do this is waveform generator is less expensive at lower frequencies. Now when we receive the signal back at 1.5 gigahertz, we want to down convert it back to a low frequency. And we want to do that because when we want to go digital to do the processing, it's easier to get high dynamic range for A to D converters at lower frequency. And when we down convert, we put into a mixer, again, the same exact local oscillator signal of 1.4 gigahertz, but we take the difference output from the mixer. We use the mixer slightly different. And there it subtracts the two signals, the 1.5, the frequency, 1.5 to 1.4, and we're left with a signal whose frequency, center frequency, is 0.1 gigahertz, and that would go into the A to D converter. Okay? So that's what the up conversion and down conversion are done for. The up conversion is because it's a bit less expensive to make the waveform generator, and the dynamic range issue with the A to D says, oh boy, you really want to do it at as low a frequency as possible. So that's why we do it. Let's look at this all together in a full-blown system. I've sort of built up this transmitter and receiver piecemeal. So we start off with our system with the numbers we talked about in the previous view graph. We started off with a tenth of a gigahertz in the waveform frequency in the waveform generator. We amplify it, filter it, then we up convert it to a gigahertz and a half, filter it again, then go into the high power amplifier where we make it gigantic, and then out through the switch, which is turned so that nothing gets in the receiver, and out the amplifier. And then after the pulse is transmitted, we turn the switch, the duplexer, in the other direction. Transmit is cut out, and we listen carefully, and then we filter the signal, amplify it, down convert it, and then A to D the signal. And in many cases, there'll be multiple stages. I've just shown you one stage of up conversion and down conversion, and there can be multiple stages in general in many radars and receivers in the microwave region that are used for, and we can have multiple stages of filtering and amplification as well for the reasons I've mentioned. Now let's look at the whole issue of transmitter and receiver architectures. I've talked a little bit about each of them in the past. I've shown you a picture of a tube system and then mentioned about passive arrays and active arrays. And now let's look at those architectures and say, why would we use one or the other? Okay, first let's look at dish radar systems. They are really the simpler ones in terms of a block diagram structure and how the block diagram of them, how it looks. They're really simple, obvious, the waveform generation, a big transmitter like that big room I showed you at Millstone, or that S-band transmitter with the traveling wave tubes, a duplexer, a switch, and then out a big dish. And then back a receiver and an A to D converter back to the receiver and signal processor. Dish radars a lot of the time will use, most of the time, a lot of the time, but not all, will use these transmitters. With dish, we'll use single tube transmitters. Okay, and this is a block diagram of what it looks like. What are the attributes? Well, they're the lowest cost. But when you have a dish radar, you've got to remember you've got the inertia of that dish, and it's going to be pointing towards one target. And usually dish radars are single target systems. Okay, and you can also change frequency pretty readily with dish radars. You've got 10% bandwidth you can have with that kind of a transmitter. It's pretty easy to get bandwidth inexpensively with the dish radars. The cons are they've got a dedicated function. They're going to do one target at a time pretty much. At least one angle they'll be pointing at. There may be within the range swath a number of targets, and they're going to have a slow scan rate. If you've got a target in front of you, right on bore sight, straight out, and then another target that's 30 degrees away, some of those big antennas have a huge amount of inertia. It takes giant torque motors to move them, and there's a finite time to move all that mass, the moment of inertia, over in a graceful manner that doesn't grind the gears and literally destroy them. You can't have infinite accelerations with these torque motors, or infinite torques, so you can't just go boom, boom. So and you're going to need that custom transmitter, and there are pretty high losses. The losses are the highest in this. Now, as time progressed, and these were radars that we still build plenty of dish radars, but it was a technology that was developed first. Then as technology progressed and people developed phase shifters, I've already talked about them. Phase shifters allow you to change when you have a set of, say, dipoles all arranged in a big patchwork. And let's just think of a linear dipole for the second here. Here we've just got 4 elements and 4 phase shifters. But the point being that we could change the phase in those phase shifters and ferrite phase shifters in microseconds. And in changing that phase, that changes where the beam is pointing. So we could track a target over 45 degrees in one direction, and then microseconds later send a burst of energy over 30 degrees in another direction. I mean, if we have a phased array that's like that PAVE PAWS radar that has both elements in both vertical and horizontal dimension, over a very wide angle, say plus or minus 45 degrees, we could send beams out in every which direction, every tens of microseconds being the time to change the antenna's pointing. Of course, it's going to take time for the pulse repetition rate. So, and so it takes a certain amount of time to do the process of transmitting the pulse and listening for the echoes. But the actual time of moving the beam can get very, 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 very small. And the first thing people did was they just implemented phase shifters. Okay? They had the tube antennas, and they used what's known as a corporate feed, a set of waveguides that would branch out to different places and feed, and like the trunk of a tree. They might have one transmitter taking care of one quadrant of a phased array, another transmitter taking care of another quadrant, and then the waveguide would branch out with a 3-to-1 feed, and then another 4-to-1 feed, another 4-to-1 feed, like the branches of a tree, so that microwave energy would finally get to the phase shifters, and then the phases would be changed and the energy radiated, and to generate the beams on transmit or receive. Okay. Now, what are the attributes of this system? Okay. You've got your beam agility, so you can move your beam around quite fast, and you can effectively manage your radar resources, an attribute of having the good beam agility, the superb beam agility. These are higher cost. You've got that whole microwave feed structure here still, and we've got the high cost of the transmitter and a complex feed system. When you only have the feed going out to one dish, one parabola to one feed, it's a lot less costly than the microwave that has to work its way out to all the different elements in your phased array. So it requires a custom it's much higher cost, but it's not as high as the next one. In other words, you pay for what you get. It's got high losses still, because it has the transmitter and receiver the tube type, which innately have higher losses than the solid state systems, and it requires custom transmitter and high power phase shifters. Okay, remember, we're doing this phase shifting at quite high power. Okay, now when we go to an active array, that means we have individual transmit receive modules behind each radiating element. Now, I'm going to show you in the next view graph what that is. But let's first look at the attributes. We're going to have the beam agility. Great. We're going to have effective radar resource management, as before. We're going to have lower loss, because we're not going to have the losses associated with the corporate feed. The whole transmitter and receiver will be right up there in the antenna. But it's a much more complex and costly system, the most complex and costly, but it does the most. You're going to have a very complex cooling system, because instead of having water or ethylene glycol, a common cooling fluid, pumping through that huge Klystron, which is a rather centralized cooling system, we're going to have a cooling system that's going to be distributed all over the face of a big phased array radar. So the cooling system is going to be much more complex. And there's a much higher cost for all these individual elements. Okay? And we've shown pictures before of a lot of the different radars. This is like the Millstone radar. This is like the Aegis radar. And this is like the PAVE PAWS radar. You know, that's a nice way of moving down the line. Okay? Now let's look a little bit about what the active phased array elements really are, so you can see a little bit better. Those little sections in I'm blowing them up so you can look at it. So with each transmit receive module, the core, I'll say, the core of the phased array radar is each transmit receive module. Okay? Now, and notice what we do is we have a waveform generator, which will send at low power signals out to the transmit receive module, which has a low power section and a high power amplifier, which generates high power, but not at all as high power as that big tube. Remember, these solid state modules generate tens or hundreds of watts of power per transmit receive module, and each one of the modules will have its own duplexer. And in each active TR module, there'll be its own receiver, and the switching back here, these are a lot of these lines are control lines, which says, okay, turn on the transmitter, okay, listen to the receiver. So, and the data will go back through those lines, okay? And this is the switch to make sure there's isolation, okay? But way back here, we have the waveform generator, and it will send signals out to the different subarrays with the information about what the phase shifters should be doing. And notice that the transmit-receive function, the big bottom line here, is it's distributed to each module on the array. And likewise, the receive function, as the transmit and the receive, is distributed. The receive echoes will come back, and then they're already gone through the receiver, so they're back at baseband, be added together, and then they'll be digitized. Okay, here are some pictures of some large phased arrays, just to show you. I mentioned before, Aegis is a passive array system with 4,000 elements at S-band. This is the Theater High Altitude Area Defense Radar, a missile defense radar. It's got 25,000 elements. And Cobra Dane is a passive array radar that is built by Raytheon. It was built over 20 years ago. And it has 15,000 active elements. Okay, so here are some examples. They're pretty big, physically, and with lots of elements. And Cobra Dane is at L-band, THAAD is at X-band. Okay. Now there's another way you can push stuff up into the front end, and that is you can go digital on receive. Okay, and this is going to allow you to form multiple beams. What we do is we generate our signal, transmit it as we would in a standard phased array radar. And what we could do is we could take from our TR module the signal coming back, combine it in the A to D here, and generate one digital beam with an analog array. And or what we could do is we could take the signal from each module, digitize it right up at the module, and then back, instead of generating one beam, we can have a multi-channel digital beam former, a device which will generate not one beam, but multiple beams. So if we have a transmit beam that's fairly wide, we can generate a number of different receive beams that could look at different places within that transmit beam. And each active analog TR module is followed by an A to D for immediate digitization. So we can so it allows us to make multiple beams, and the different beams can perform different functions or simultaneously do surveillance over different pieces of coverage. Okay? And RSTER, the system I showed you a little earlier, that solid state system uses digital on receive technology. Okay. Now the next thing that we can do is we can, the last subject I'm going to dwell on, is that we can transmit and receive digitally. That is, we can have our waveform control, and then up in the transmitter, we can digitally generate the transmit signal right up in the TR module, so that we have digital on transmit and receive. Okay, so both waveform generation and receive digitization are performed within each TR module. And that gives us complete flexibility on transmit and receive. It allows us to do an enormous amount of sophisticated signal processing, and adaptive signal processing techniques that are just very, very useful. Now I'd just like to summarize. The radar transmit function, I noted, is accomplished in two stages. First, we generate the waveforms at low power, then upconvert to the RF, to the microwave frequencies, and then we amplify in the transmitter to generate the signal that we transmit. The receiver is where we receive the signal, filter, amplify, and down convert. And these received signals are then digitized to get ready for the signal processor and the detection lectures we've already gone through. And how we develop the transmitter and receiver architecture is very, very dependent on the antenna type that we use. We can have a centralized architecture like dish radars and passive array systems, or distributed architectures such as active arrays and digital array radars. Well, now lastly to the last view graph in the whole course. These are the references for Chapter 10. Well, I'd like to thank all of you viewing the course, the persistence that it takes to spend this amount of time, and I hope that the course has been very useful to you, and it will be useful to you in the future, and that you've learned an awful lot about radar systems. Thank you.